Hey guys, how's it going? I wish this lecture reaches all of you in a healthy well-being. So despite the fact that today I will start a new module, I would like to emphasize again about a question I received from one of your classmates, which is asking me about the universality of NAND and NOR gates. So let's get started. So guys, imagine you are a designer engineer, or imagine you are at interview at one of the most prominent silicon companies such as Intel and AMD. And at the interview, they ask you to design a logic circuit to generate a signal X that will go high whenever conditions A and B exist simultaneously, or whenever conditions C and D exist simultaneously. So, as we can see here, the logical expression for function X can be expressed as A and B, because look here, it's A and B, or C and D. So the engineer from Intel told you that you have three types of integrated circuits, ICs, all built from the transistor to logic architecture. And these ICs have the component number 74LS32, that is for OR gates, and 74LS00, that's for NAND gates, and 74LS08, that's for AND gates. So as you can see, guys, each one of the ICs has a quad gates with 4 identical gates, as you can see here. Okay, we have 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay, those are ORs, those are NANDs, and those are ANDs. Now, so how can we design this function X knowing that we have these three ICs? Yeah, it's worth noting that those ICs can be ordered, guys, from websites like Amazon or Jamico, as you can see here, So the question is, how can we implement function X based on the available ICs that we have? So one possibility to do so is by using the IC for the AND to implement the minterms AB and minterm CD, and then we OR them. Okay, so the way to do so, we can use the pin 1 here and pin 2 here to implement AB. Okay, and the resultant will be the output will be at 3. And we can use the pin 4 and pin 5 to carry the inputs for CD, and the resultant will be on what? The output will be on C. Then we have to use another type of IC, which is this type, okay, to OR both of the signals that are coming from 3 and 6. So we can do a junction or a wire between 3 and 6 to 1 and 2, and then we can get the output here. Okay, now let's suppose that myself, and let's say who's in the class, let's say Jason. we implemented that. And we have another implementation implemented by IHAM or Russia, and it's based on the De Morgan law. So suppose that x equal a b plus cd, applying De Morgan law, that will be equal to ab prime plus cd prime. The whole term is, the whole expression is prime. So we will benefit a lot from this implementation. Why? Because we will not need to use the other two type of ICs. The same IC, actually on the same chip, we can connect A and B at 1 and 2 here, and the output will be at 3. And we can connect C and D on 4 and 5, and the output will be on 6. And then what you can do is make just a jumper between 3 and 9 here, guys. 3 and 9, just a jumper, or like a junction, you know. 3 and 9, and a junction between 6 and 10, okay? And the result will be at 8. So basically the whole term, the whole Boolean function x is implemented just with one single IC. That's why both NAND and NOR gates are called universal gates or functional complete gates. Okay, guys, that's it for the guy who asked about why NAND and NOR gates are called like universal. Okay, so as we discussed on the review session, like I mentioned that anything when it comes to our science can be modeled through a mathematical equation. So can you, professor, provide us with a direct equation to calculate the cost? I don't want to just guess and try to simplify and guess again. So the cost of implementing a logic circuit is related to the number of gates used and with the number of inputs at each gate. Okay, so from that statement, what we can propose that the cost to implement any Boolean function, and the condition that this Boolean function has to be in the format of the SOPs at the sum of products, will be given by the sum of the cost to implement the terms and the sum of the cost to implement the literal. Again, guys, the literal is the Boolean variable or its complement. So what are the rules to calculate the cost of the Boolean function? So the rules are so simple. So we count how many terms this function has. If it has only one term, the cost to implement the term will be 0. Okay? If it has more than one term, the cost will be the number of terms that that function has. And similarly, we look at each term and we will see how many literal per each terms, how many literals per each term. If it's just one literal, then the cost to implement that term will be 0 because it's simply a wire. But if the term has more than one literal, then the cost to implement that term will be the number of literals. So let's take a look on this function. So what will be in your imagination the cost to implement function f1? Okay, according to this equation. So this function, guys, how many terms it has? It has two terms. And how many literals? So per each term, here we have this term has 4 literal, and this term has 4 literals, which are xy prime z plus xy y z prime plus, And how many terms per this function? We have 2. So the cost to implement this function will be 4 plus 4, 8 plus 2 will be 10. Okay, guys? Okay, so what about another examples? So let's suppose I would like to calculate the cost of function f2. So function f2 is a tricky one because it has 1, 2, 3, 4 terms, okay, both at the, the sum of products notation, all of them at the sum of product notation, and it has, the first term has only one literal, so the cost to implement that term will be equal to 0. And the cost to implement the second term will be equal to 0. This term unfortunately has 2 literals. As such, the cost to implement them will be 2. And the cost to implement this one again will be 2 again. Therefore, guys, and we have 4 terms, and this function has 4 terms. Therefore, the cost to implement this will be equal to 8. Okay? Now, what about the cost to implement function G1? Now, the cost to implement function G1 will be like this term has 2 literals, this term has 2 literals, this term has 2 literals, and we have 3 terms. Okay? So 2 plus 2 plus 2 plus 3 will equal to 9. Okay? What about this one? 2 terms, 2 literals, 2 literals, and 2 terms. So 2 plus 2 plus 2 will equal to 6. Now what about this one? And that's why I would like to emphasize on this H1 and H2. Okay, so H1 has 1 term. Therefore, this the cost to implement the term will be equal to 0. Why? Because this function has just the cost to implement it will be equal to 0 because this function has only 1 term. Okay, and the cost to implement the term will be the number of literals, and unfortunately this term has 2 literals. Therefore, the cost will be 2 to implement the literals plus 0 will be equal to 2. See that? And for the last one, this function has 1 term which is 1 literal. Therefore, the cost to implement the literals per the term will be equal to 0 as of this. And the cost to implement the terms will be equal to 0 because of this rule. Okay? Therefore, this cost to implement function H2 will be equal to 0 because simply function H2 is simply a wire. Okay, guys, let's go and okay, guys, if you remember the last question we solved together at the review session, which is designing a logical circuit at which the output will be high as long as 2 of its inputs are equal to high. So the output F will be equal to 1 if 2 or more inputs are equal to 1. Okay? So if you remember the way that we solve it, first we started by writing the truth table, and since we have 3 inputs, we have A, B, C, and here it's gonna be 0, 1, 0, 1, 0, 1, and then 0 and 1, and here it will be 0, 0, and here it will be 1 and 1, 0, 0, 1 and 1, and here it will be 4 zeros and 1, 1, 1, 1. So the output F here will be equal to 1 as long as we have 2 or more inputs are equal to 1. which is in our case, this will give me 0, this will give me 0, this will give me 0, this will be 1 equal to 1, will be equal to 0, this is 1, and this is 1, and this is 1. So the function f can be rewritten as the sum of 3, 5, 6, and 7. So if you remember that we wrote this function in terms of a minterm as a prime b c because of the 3 plus a b prime c plus a b c prime plus a b and c. So if I wanna simplify this function, and I can take here the common factor will be in my case here, which is I can take here I can take a b as a common factor, and this will be c prime plus c. And here what I can do is I can take nothing. Okay, as you can see, I can take nothing. A prime bc plus a b prime c plus this, and this will give me 1, so it will be a prime bc plus a b prime c plus a b. Can I go further? No, I cannot. So if you are unlucky and you are at my shoes right now, and you did not realize that this term ABC has two variables in common with each one of my terms, and you did not add 3 copies of ABC to simplify it, you will get stuck. Okay, let me show you again. So we got here a prime bc plus a prime a b prime c plus a b c prime plus a b c. As you can see, this term here has 2 variables at which, if I use it, I can take 2 variables as a common from each term here. So away from that, like if I say x plus x, it still be equal to x. Therefore, I can copy this term 3 times. Okay, so a prime bc plus abc plus a b prime c plus abc plus a b c prime plus a b c. So what I can do here, I can take bc as a common factor, and this will give me a prime plus a, and here I can take ac as a common factor. Okay, and this will give me b plus b prime. Okay, and for these I can take ab as a common factor, and I can get rid of c. Okay, c plus c prime. So that function, the simplified function, will be ab plus ac plus bc. So not a lot of you will be able to catch this. Okay, so please pay attention to that. However, the key point that I'm trying to reach here, I'm trying to say here, is that is there any other effective way to simplify the function without the hassle of remembering all the theorem and the postulates? The answer will be absolutely yes. So that effective tool is called Kernoff maps. So a scientist, an American physicist, who is, by the way, was working here in Canada at the Bell Labs, came up with this article at which he invented a graphical tools that will help you minimize any logical equations. So the kernel of map basically is a graphical tools used to simplify a logic equation or to convert a truth table to its corresponding logic circuit in a simple orderly process. Although kernel of map is very effective, here at our level, at the first year level, we're gonna limit it for maximum of 4 variables because it's gonna be nasty when we have 5 and 6 variables, and usually it will, like, those simplification will be done via a computer program. Okay, so what is a kernel of map in detail? So the kernel of map is simply a squares, a matrix, and that matrix in reality it's gonna be a cylinder. Okay, so this, at each cell of this matrix we have a square, and this square will represent a term. That term can be either a min term if we are looking for the sum of product, or it can be a max term if we are looking for what? For the product of sum. Okay, so the number of the cell or the squares of each kernel of map will be determined based on the number of variables. So imagine here we have like a function f, which is basically an OR gate. So this function has 2 variables, therefore the kernel of map of it will have 2 to the power 2, which is equal to 4 cells. Now you have to understand that, guys, the kernel of map is just a reproduction of the truth table in a graphical way. Okay, so basically that truth table can be rewritten by indicating A to be the the index of the rows and B to be the index of the column. So here we have 0, 0, that is 0 and 0, therefore we put the value here of 0 and 0 at our truth table, which is here we are indicating it by M0. Okay, and 0 and 1 here, 0 and 1 will be here what? M1, therefore we put M1 here. And we have here 1 and 0, 1 and 0, we put M2, and 1 and 1 we put M3. Okay, but guys, I would like to pay attention to the following. Now at the 3 variable kernel of map, if you would like to simplify a function similar to the one that we just did in the previous slide, here our kernel of map will be a big matrix that has 1 row and 2 columns. Okay, now because we took A as the most significant bit to indicate what? To indicate the the row, and BC will be what? Will give me the code for the column. But if we compare this map to the truth table, we can see that we're changing from 0, 0 to 0 and 1, and to 1 and 1, not to 1 and 0. That is a very important point to pay attention to it, because the whole idea of K-map is depending on changing one variable. Okay, so if we have x, y, I have to change it to x prime y, or I have to change it to x y prime. You know why? because I would like to loop, and if I loop, I will utilize the theorem at which x y plus x prime y, if I take y as a common factor, x will be deleted, so I'm gonna get y. I'm gonna eliminate the variables by looping. Okay, so the key point here is we can change just one digit of the code for either the row or the column. Okay, now the kernel map for 4 variables will be, you know, a 4x4 matrix at which it can be represented either by taking AB to represent, which is what I prefer here, AB to represent the most significant bit here, because we have it here, to represent the rows, okay, and CD to represent the column. Okay, so basically if we look here, guys, here we have 0 0, then 0 1, then we cannot go to 1 0, no, we go to 1 1, because we will only change this bit or this digit. Okay, 1 and 1 and 1 0. And for the columns, it will be the same, so 0 0 0 1 and 1 1 and 1 0. Therefore, when we are filling the map, the kernel map from the truth table, here it's 0 0 0, that's the first row here, and here 0 0 1, that is the second row here. Now here it's gonna be 0 1 1. I'm gonna go here, I'm gonna go to M3, and then after that I'll go to M2. Okay, is that clear? And we should apply that when we are, you know, looking for the row 1 1. So at row 1 1 here, we should skip, you know, we should skip M8 and go to M12 directly. And even at this cell, instead of going to M13 then 14, no, it's gonna be M15 then 14. Okay, so it's like Excel, guys. It's like, you know, a table. Okay, and you should abide by the codes for the variables. Okay, guys, so basically let's suppose that we have this truth table. We will follow this truth table accordingly in our map. Okay, if we swap the row and column, it's gonna give me the same result. However, please pay attention to the way that I filled the table. So here, because it's 0 0 0 0, it's still zeros, 0 0 0 0, still zeros. Okay, so it's M0. Now here it's gonna be like it's gonna be 0 1 0 0, so it's gonna be M4. It will be 0 1 0 0, that's M4. So that's why I put M4. Here it will be 1 1. Here it will be 1 1 0 0, 1 1 0 0. That is M12, guys. Okay, that's why I told you I prefer the first format. Okay. Okay. So what are the benefits from the kernel map? As I told you, kernel map will mainly work on the fact that, you know, if we are grouping 2 adjacent cells, we can eliminate 1 variable for sure. Okay, now let's take a look at this kernel map here. So is there any way to loop here? Now the question you have to ask yourself, how to cover all the ones in the kernel map using the largest grouping, the largest rectangles, and as a few rectangles as we can. And please note that the grouping has to be done in terms of 2 to the power n code. Okay, guys, so basically here we cannot group this and this, we cannot group diagonally. Okay, we can group either like vertically or horizontally, and we can group the corners if we can, but here we cannot do it. So that's just one and that's just one. So this one, in order to get the code of function f, as you can see, this will be at A prime, that is A prime. You remember that's a negative logic, and this is A, okay? And this is B, and this is B prime, okay? So F will be what? The combination between A prime and B, okay? Plus, for this one, it's gonna be A, B prime. Okay, is that clear? Now, when it comes to this function here, I can do a grouping in a way that I can group vertically here and I can group horizontally here. So now to get the corresponding term for this group, it will be here. You see that? Because I'm changing from 0 to 1, I'm gonna neglect A and take just the one that is constant, which is B here. Okay, so it's gonna be just B, and here is gonna be like, because B is changing and A is not changing, plus A. Okay, let's show you in more detail here. So we took this, and this will give you B, because that's 1, and this will give you A. Okay, so the F simplified will be A plus B. We'll not go over the hassle of, if we grouped each one of them, is going to be AB plus A prime B plus AB prime. And if we can use Boolean algebra, we will get the same result. Okay, so it's like a magic. Now, let's take a look at this kernel map, which has three variables. Three variables is going to be what? 2 to the power 3. So it's going to be 8 cells. Okay, that's why we have here 8 cells. Okay, so as you can see, if we would like to write this function unsimplified, what you have to do, guys, is to take the code of each one in your in your map and neglect the zeros. So the code for this one will be, here I have A, and here I have what? 0, 0, 2 for BC, so it's gonna be B prime C prime. Okay, so that's why the first term will be A, B prime, C prime. Now, when it comes to this one, what's gonna be? That will be A prime, because it's at A equal to 0, and B prime because B is equal to 0, and C not the prime. Okay, so C, so it's gonna be A prime, that's one, it's gonna be A prime and B prime and C not the prime. Okay, C. And for this one, so what will be the code for that? It will be A, again, B prime, C. Okay, and for let's say for this one, what is, what's the equivalent term for this one? It's gonna be A prime, because at row A prime, and B, okay, true state, and C prime. Okay, now by looking at this, can we group them in a group, like that contains most of the ones, and this groups contains like cells that is 2 to the power something? Yes, the answer is basically yes. So what can, like this one here can be grouped into, and this one here can be grouped into, this one here can be grouped into, and this one here can be grouped into. And look at, I found something here, so I can neglect those 2 and group them in 4. Okay, therefore look at this, guys, you see that? So I grouped all of them. I'm looking for the largest rectangles and as few rectangles as I can. So instead of grouping these in 2s, what I have to do is group them in 4, And for those two poor things, I will group them into. Now, in order to get the code for this, quad ones, what's gonna be the code for that? It's gonna be just A, because look, B, C, they're changing all the time from 0, 0, 0, 1, 1, 1, and 1, 0. So I'm gonna neglect them. Okay, so it's gonna be just A, and for these two, A is changing, I'm gonna neglect it, so it's gonna be B prime and C plus B prime and C. And for this one, A again is changing because I'm going vertically, so A is changing, I will neglect it. And then I will have just here is gonna be B C prime, okay? B C prime. Okay, guys? Now, let's apply what we learned in a real life example, okay? Now, let's suppose that you need to design a 1-bit adder and you want to design it using the kernel map. So what's the 1-bit? And by the way, this is a full adder. So the difference between in digital logic, we have either a full adder or we have a half adder. The full adder has 3 inputs, A, B, and C in, and has 2 outputs, sum and the C out, okay? Whereas the half adder here, and you can say it's half adder like this, it just has A and B and has just 2 output, okay, which is the sum and C out, okay? So the most wider one is like what? The full adder. Why? Because the full adder is capable to add 3 bits at the same time. Like suppose that you wanna do this, you wanna add 1 plus 1 plus 1. Can you do it on the half adder? Here you attach 1, here you attach 1, but where are we gonna attach the third one? There is nothing, so that's why we need the full adder, okay? Okay, guys, so we need to to design an adder, and that adder is being symbolized by this, and this box has to be changed by some logical gates, so we don't know them. So remember, what will be the first step to design any digital circuit is to construct the truth table. So this function, this circuit has, look at this, has 3 inputs, A, B, and C in, and has 2 output because we need to calculate the sum. In our case here, let's suppose 1, 1, 1, we will have the sum of 1 and the carry out of 1, okay? So, and we will go over the possibilities at the truth table. So the possibilities are like, if we added 0 plus 0 plus 0, the sum will be equal to 0 and the C out, the carry out will be equal to 0. That's something we covered at module 1, okay? So 0 plus 0 plus 1, then what will be? The sum will be equal to 1, whereas there will be no carry out. That's why I put 0 here, okay? Now, what about 0, 1, 0? It will be the same. Like sum will be equal to 1, the carry out will be equal to 0. Now, 0, 1, 1, that is my case here. 0 plus 1 plus 1. So what I will have here, I will have 0 at the sum, and then I will have a carry out. Okay, so 0 at the sum, and I will have C out here, carry out, okay? Therefore, that's why I put 0 and 1, okay? And here it's gonna be just the sum because I have just 1. And here it's gonna be just the C out because I have 2. And here it will be just the C out because I have 2. And here I have the case of 1 plus 1 plus 1. Then I will have a sum and I will have a carry out, okay? Now, the way to, if you wanna, guys, if you would like to just write the output S in terms of a sum of product format. So the output S is what? is 1 here, and 1 here, and 1 here, and 1 here. So it has how many min terms? 1, 2, 3, 4. That is M1, okay, and that is M2, that is M4, and that is M7, okay. So we write those terms in the code of the sum of the sums of products. So to indicate M0, it's gonna be M0 A prime because A is equal to 0, B prime, and Cn not prime. You see that? And for M1, for M2, it's gonna be A prime, B not prime, okay, B, and Cn will be prime, and so on, okay. And for the Cout is active high is equal to 1 whenever I have at M6, no, at M3, sorry, because that's equal to 3, and here at M5 and M6 and M7, okay. So M3 will be A prime BCN, A prime BCN, and M5 will be A B prime Cn, and M6 will be A B Cn prime, and M7 will be all of them at the one state, so A B Cn. Now, if that equation reminds you exactly with the example I just did, you know, here what can I do? How can I get this Cout to be minimized as BCN ACN plus AB? You remember what you have to do, guys, here. If you did not catch the fact that this term has two variables in common with the other terms, and you have to duplicate it 3 times, you will be in trouble, okay? So you have to add it 3 times in order to take like each time like two variable as a common factor, and then, you know, delete the variable plus its complement, which will give you 1. Okay, let me show you here. So that's exactly what will happen. Okay, so I repeated this how many times? Like 1, this is 1, and I repeated here 2, and I repeated here 3 times. Okay, so and then what will happen is here I can take, as you can see, I can take here what BCN as a common factor, and for this one I can take ACN as a common factor, and here I can take AB as a common factor, okay? And that's it. With that being said, this A will be equal to 1, this B will be equal to 1, and this Cn prime will be equal to 1. So in other words, I'm gonna get, this term will give me just BCN here, and this will be ACN, and this is ABCN, okay? This will be just AB. So now the question of the $1 million. Can we use Karnaugh map instead of this tricky Boolean algebraic simplification? The answer is basically yes. Okay. So to do so, what we have to do, we have our truth table, and that will be our real example. So what we have to do, guys, is here it's the Karnaugh map for Cout, okay, for the output Cout, okay. So what we have to do, I have here a Karnaugh map, and this Karnaugh map has what? Has B here, okay. I'm showing you in a different style. B, imagine B will be at the row, and ACN will be at the columns. So we have 0 and we have 1, and here we have what? And here we have 0, 0, 0, 1, and here 1, 1, and 1, 0. That's why, because I have ACN, that's why this will give me A, and that's why that's just for B, and that's why that's just for Cn, because look at this, Cn equal to 1 at the code of ACN here. Okay, now what I have to do is I have to fill my empty squares with just the ones. Okay, so here my C out will be equal to 0 at all of them 0, so I will put 0. Okay, and here my C out is equal to 0 at 0, 0, 1, so I'm gonna put what here, 0. And then at M3 I have 0, so what I'm gonna put here, I'm gonna put 0 here, guys. Okay, because you know the code again, it's A, it's B, A, C, N. Okay, I just did that because I want to show you that the kernel map will work regardless of any code you follow, but you have to stick with it when you fill. Okay, now let's go here and pay attention to what will happen. Okay, we are at the like M3, and it's gonna be 1. Where I'm gonna put M3, guys, where I'm gonna put M3 will be put right there. Okay, and then at M4 I'm gonna put 0, and here I'm at M5 I'm gonna put 1. Okay, and then at M6, which will be here, I'm gonna put 1, and M7 here I'm gonna put 1. Okay, so now what is the question? The question is how to cover all the ones in the kernel map using the largest grouping. The grouping will be like here as a rectangle. It's a loop. How we're gonna loop, and as a few rectangles as we can. So this poor guy can be grouped just once, just this way. So I have to group it, and this poor guy can be grouped just in one way, and this poor guy can be just grouped in one way. So then this guy is already covered. It's grouped either here or it's grouped either there. Okay, okay, so this, guys, will give me what? That group will give me, because that's indicating A, so it will be A, and because B is not changing, it's gonna be AB. And for this one B is changing, so what, it was 0, then it becomes 1, so that was, I'm gonna neglect B, so here it's gonna be ACN. Okay, because remember that is 1, 1. Okay, so ACN. And for this one, B is not changing. Okay, so B for sure is gonna be N, and this is 4 and 0 and 1, and here and Z, and here it's 1, 1. What is not changing here is just the CN. Okay, that's why I chose that. For the sum, guys, the process is still the same. So what we have to do is we have to go and look at this column, which represents the sum output, and then replace the output here, the zeros and the 1, into the corresponding kernel map. So remember, guys, this kernel map is coded as the following. Here we have B, and here we have A and Cn. Okay, so here it's gonna be 0 and 1, and here it's 0, 0, 0, 1. Now here it's 1, 1, and 1, 0. So what is not changing here, guys? What is not changing? It's clearly it's the A prime. Okay, and what's not changing here, guys, between those two adjacent columns, like it's clearly that is not changing, is the what? The Cn. Okay, that's why I put Cn here. And for this one, for these two, what's not changing? What's not changing is those ones, 1, 1. So that indicate A. Okay, guys. So at 0, 0, 0, okay, here. So we have here 0, 0, and 0. I'm gonna put 0 because the sum here was equal to 0. Okay, at 0, 0, 1, which is here 0, 0, and 1, I'm gonna put 1 because the sum was equal 1. Okay, guys, and so on. So after that, I'm gonna try to answer the questions. I have a function S, and it has 3 inputs, and it has a kernel map with 8 cells. Can I group all the ones in a group of 8? The answer is no, because unfortunately I have zeros here. So can I group them in a group uh, of, of 4? The answer is no. I cannot group this one in a group of 4. I cannot group this one in a group of 4. I cannot group this one in a group of 4. Now, okay, so I'm gonna lower my bar and ask myself, can I group them in a group of 2? Remember, I told you we cannot group the ones diagonally. So what will happen is I have to group each one of them individually. And when I group the like each one of them individually, I will get something equivalent of the standard notation, the sum of a product notation. Therefore, if I try to group this one here, so this one will give me like here, B is at the true format, and here I'm gonna have like A prime, C in prime. Therefore, I'm gonna get A prime, B, C in prime. And for this one, here, B will be at the row B will be at the B prime because this is 0 and this is 1. Okay, so that is B prime, and here it's 0, 0, and 0, 1. So it's A prime, B prime, and Cn. Okay, and for this one, B is at the true format, and remember that's 1, 1. So it's going to be ACN. Therefore, it's going to be ABCN. And for this last one, it's B at the like at the complement format, and A is at the true format, and Cn will be at the complement format because that's 1, 0. Okay, so A, B prime, Cn prime. Okay, guys. So as you saw, we implemented the output, like the carry out, as well as the sum for this 1-bit adder. On module 4, we're going to see how we can cascade them in order to do an addition for multiple bits. Okay. Okay, so let's go and cover something else. Do you remember, guys, in module 2, we covered this exercise at which we calculated the complement of this function. This function has 4 inputs. So does kernel maps will make it easier for us finding the the complement without the hassle of going through all over the Boolean algebraic theorems and postulates? That's what we will see. So our function, guys, if you remember, it was Wx and multiplied by the OR between y prime z and yz prime. And I told you that was an XOR. So what we have to do is we have to write it in the sum of products so we will know exactly how to represent it. Now that's what I'm going to show you, how we can represent those min terms directly on the map. Okay, so after applying the distributive law, which is just simply multiplication, we have this term and we have this term. And I want to map them directly to this kernel map. And why did I choose a kernel map with a 16 cell? Because simply here, guys, if you see that function has 4 inputs. So 2 to the power 4 will mean 16, okay? Okay, so this map here has X here as well as Z to indicate the rows, and W and Y to indicate the columns, where this will be 0, 0, this will be 0, 1, this will be 1, 1, and this is 1, 0, and this will be 0, 0, 0, 1, 1, 1, and 1, 0. Now the 0 here will indicate y prime and w prime. Here it will be w prime and y. Okay, so basically when we are looking for this term, guys, what we have to do, we have to shrink the area we're gonna place our 1 into it, because we're gonna look where w is at the true, so it's for sure at one of these two, at at a cell belongs to one of these two columns, as well as at x at the true format is gonna be at the cell at one of these two rows, and y prime, so y prime, okay, y prime is gonna be either here or either here, and the deal breaker will be z, so z will tell us I'm gonna be like at my true format at these two rows. Therefore, where do you think our 1 will be? It's gonna be here. So that is why I choose this one. Okay, it's gonna be right there. Okay, now for we will do the same when it comes to the other term, which is wx yz prime, and instead of that we're gonna look somewhere either here and somewhere either here because of the z prime. Okay, but so what we have to do, we negate that because we have x at, we negate that row because we have x at the true format, so we have to look here, and then what we have to do is it's gonna be for sure here. Okay, so now the question is, how do we build the kernel map for the complement of our function? That's the kernel map for function f. The answer is so simple. What we have to do is to fill ones everywhere, and for those two ones we will put zeros. Okay, okay, now the questions that we have, since we obtained the kernel map, the question that we have to answer is, how can we group this kernel map to give me the simplest form of f prime? Okay, so since this kernel map has 16 cells, we will try to look to group all the ones in a group of 16. But since we have 0 here and 0 here, that option is not on the table. Okay, then we're gonna lower our bar and look for to group all the ones in a group of 8. Can we do that? Of course we can, because this one can be grouped in a group of 8, and similarly to the other ones. So that's why I decided to go and group them. Okay, when I group them, guys, when you group all the ones in a group of 8, you're gonna eliminate um, uh, all the literals and keep just one literals, because you're taking something that belongs to what, x prime. X prime is the only thing that's not changing when you are sliding in to the column, or when you're sliding down to the rows, because that is 0, 0, and 0 and 1. So it's only like x that's not changing. X, that's why we choose x prime. However, when it comes to the column, look at this. It's 0, 0, 0, 1, 1, 1, and 1, 0. So like when we move here, like now we're gonna exclude what? We're gonna exclude y, because y has changed. Then when we move from here to here, we're gonna exclude w. So that's why we choose just x prime. Okay. Now, can we group another one in a group of 8? Okay, from the one that we did not group? The answer is yes. This one can be grouped in a group of 8. That's why I choose to group it. And when I group these, look here, because you're going at all the rows, you should exclude them. Now, what is not changing here? Remember that is 0, 0, and 0, 1. So what's not changing here? It's simply, guys, w prime. That's why we wrote w prime. Now, can we group the remaining ones in a group of 8, unfortunately, we cannot. So we will lower our bar and we will choose to group them in a group of 4. Can we? I see here, yes, I can. I think this one can be grouped in a group of 4 by doing this. Okay, that's what I'm gonna do. So that one will be grouped in a group of 4 to get the to get the like the code for that term. It's like, or for that implicant, in other words, it's gonna be what's not changing here? Z for sure, not changing. And what else that's not changing? It's gonna be not changing here. I'm gonna go here, it's Y. That's why I choose YZ. Now this one is the tricky one. Remember I told you, like, Karnaugh map, even though it looks like a cube, but it's like a cylinder here. Okay, so that's why I will be able to group these for Y, because look at what is the code for this cell? That is 0 0. What's the code for this cell? Okay, that the code for this cell is what? 1 0. So look here and here, we're not changing what? We're not changing the Z. Okay, and when it comes to this one and this one, what's the code here? 0 0. And what's the code? It's 1 0. What's not changing here? What's not changing here? It's the Y prime. Okay, okay guys, so as you can see, we got, by doing just Karnaugh map, we got the result for the F prime equivalent to applying more than 5 theorems by Boolean algebra. Okay, now guys, let me conclude my presentation today by indicating something. Like, have you noticed, I think you noticed me like saying terms, implicant. So what is the difference between the terms and the implicant? So any single one or a group of ones in Karnaugh map is called an implicant. So if you're doing a Karnaugh map for function f, any one or a group of ones is called an implicant. The important thing is what's called the prime implicant. So the prime implicant, it's the term, like a product term is called the prime implicant of f if it cannot be combined with another term to eliminate a variable. So if you remember here when I showed you here for the sum here, like those ones are called the prime implicants because we cannot group them to eliminate anything. However, here, guys, here we could have, like here, let me show you something. Here we could have grouped all these ones to eliminate even the literals in the term, because we got at the end x prime. So that's not a prime implicant, okay? Okay, guys. So I would like each one of you to solve this exercise here, which will be posted in a private space. That's for me, guys. I will leave you with my digital twin to summarize the procedure of completing the K-map simplification process. Have a nice day.
The process to perform a complete K-map simplification is summarized by: Step 1. Construct the K-map and place the ones in those squares corresponding to the ones in the truth table. Remember to place zeros in the other squares. Step 2. Examine the map for adjacent ones and loop those ones that are not adjacent to any other ones. These are called isolated ones or prime implicants. Step 3. Next, look for those ones that are adjacent to only one other one. Loop any pair containing such a one. Step 4. Loop any octet even if it contains some ones that have already been looped. Step 5. Loop any quad that contains one or ones that have not already been looped, making sure to use the minimum number of loops. Step 6. Loop any pairs necessary to include any ones that have not yet been looped, making sure to use the minimum number of loops. Step 7. Form the OR sum of all the terms generated by each loop. Please be advised that when the largest possible groups have been looped, only the common terms are placed in the final expression. In addition to the grouping, or looping may also be wrapped between top, bottom, and corners. That's it. Goodbye.